certificate, key, and the card at TMD. Each partition is basically a title. It's a title turned into a huge block of data on the disk. Now, this is really interesting because you can't verify as 4 gigs of a game when you boot it. That's impossible. It would take forever. So what they do instead is they have a hash tree, which means each sector is signed. Then they put those signatures in a list. They put those in a big block. Then they sign those blocks, put them in a list. There's a little tree such that you can read a sector, read the signatures for that sector, and then you can verify those signatures at the read time. So they actually sign every single piece of data in a game. You can't change anything at all without breaking the signature, and it's still efficient because it's accelerated in the hardware. So it's really interesting. Like, most other consoles don't do this. The root of the signature is a TMD, which is, as we said, RSA signed, and the ticket has the key. So, why is this jumping? Sometimes there's a button that switches like 20 slides forward because I'm like that. Okay, moving on. Okay. The IOS, as we said, is a custom microkernel OS. It does most I/O, so it does all the peripherals that are connected to the Starlet go through IOS, and then Broadway can use it through an API. So there's an IPC interface that you can pipe commands between them. It even has a high-level network API, so you actually do BSD sockets over this interface. It's the entire TCP/IP stack is on the Starlet, which is pretty interesting because they can both use it at the same time. It does, of course, decryption and authentication, and it does the file system, which is on the NAND, which is kind of like Unix but cut down file system. It's got permissions. The users are title IDs. The groups are defined in the TMD, and IOS keeps track of what permissions the Broadway has. So each game can access its own save files and things like that, and they're all protected between each other. And Broadway can't see system files, which would be bad. It also controls the memory limits. It can steal some memory from Broadway and tell it to, I'll keep this for myself and you can't touch it. It's got a modular architecture. The drivers are processes. It's like an operating system. It's got a system call interface internally, and so you have like a DVD driver and all that stuff. It's separate processes.
Microkernel architecture.
Yeah, it's a microkernel. So almost all the processes talk using standard system calls. The kernel itself runs from an SRAM that's built into the Starlet, but then the user space steals memory from the Broadway. That's so the 12 megs of MEM2, which is the 64 megs of RAM, are used for IOS, and everything else can't touch them. Well, actually, peripherals can touch them, but not the Broadway, so you can't modify anything there. So, I mean, this is a pretty secure system for the most part, but that's the theory. I mean, it's designed to be secure. The question is, can it be implemented securely? So I'm going to hand over to Bushik now.
The answer, of course, is no, not so much. So the way that we broke in was something that we called the tweezer tech, hence our name. As I mentioned before, the thing was from the beginning, this device was backwards compatible with a humongous library of GameCube games, which means they could make very few changes to add more security to it. So all that code's unsigned. The idea is that they just sandbox it, and so that you can't use any of the new Wii features. So for example, you could have a GameCube game, and it puts stuff on the screen. It can read your GameCube controller, but it's not going to be able to use your Wiimote. It's not going to be able to use the SD card or talk on the network. So, and it also runs at half the clock speed, which is what the original GameCube ran. Again, the DVD drive is actually pretty similar to the one the GameCube had, which was pretty funny because it meant that the mod chip makers were able to almost immediately just port over their existing GameCube piracy designs to work on the Wii. Now, some of you may remember TMB Inc. slide that said, insert mod chip here. Well, it was a little bit harder than that, but not that much harder. So we were actually able to run some homebrew GameCube when using these chips, but it wasn't so interesting. It meant we could take something that would run on a GameCube and run it on a Wii, which doesn't really do much more than running on a GameCube. So you weren't able to access any of those features. And the way this is actually implemented is that the Wii always boots off of its NAND into this wonderful system menu, and then on the menu, you go to your little disk channel, and you put your GameCube disk in, and it says, oh, it's a GameCube disk. I'm going to reboot the PowerPC into GameCube sandbox mode. And the GameCube mode uses both of the memory banks we mentioned earlier. There's a main Mem1 area, which is 24 megabytes. Then there's an external chip that's 64 megabytes. And the GameCube only uses 16 megabytes of it as audio RAM. And the actual implementation of this is crucial for the next step. Tweezer attack. So, once you reboot into GameCube mode, you can read the lowest 1/4 of this external memory chip, this 16 megabytes of memory. You're not allowed to read the other because the Starlit iOS Hollywood contraption protects against that. You just get random garbage if you try to read it. However, I guess because of this, they didn't bother to think they needed to clear this memory area after rebooting. So, as I said, you start out in the system menu and it says, oh, you're a GameCube game, so I'm just going to reboot you into this mode. So they left all of their crap up there in the upper 48 megabytes. Normally you can't get to it. However, it is a chip. And so the chip has address lines like many chips do. And so if you go there and you start tweaking these lines and connecting them high or to low, you can actually change what it is that the Wii thinks it's seeing. With this, we were able to temporarily move around our little 16 megabyte window of memory throughout this entire 64 megabytes of memory. We were able to do this, and TMBink did this, and he soldered up to his little GameCube controller port and bit-banged 64 megabytes of data. Oh boy. 64 megabytes of data out to...
It's the remote that has keys that just press all at the same time.
Should have used Keynote. So TMBink is the one that actually did this, and he soldered to his little controller port and bit-banged, painstakingly the entire memory just out that little port. And we were able to go look through it and, oh wait, they're storing all the keys there in that memory, which was a huge mistake. I think they'd agree with me. So, as far as what we discovered when we found keys, it turns out that each console has some independent keys. And this is important because one of the early attacks that people had tried was they said, oh, well, you have this little NAND flash memory chip on a Wii. Well, maybe I would buy some games and then want to give my friend, I want to give Mark and all of my VC wares I got. And so I'm just going to copy my chip and hand him a copy of my chip. And that just doesn't work. And the reason why is because there are several different keys that are stored inside the Hollywood and that you can't just copy that way. One of the interesting things that they did was they gave each console a private key using ECC, which is a little bit like RSA, and it's a public key system that you can use for signing things. In order to verify that this is a legitimate key, there's a certificate that is signed by Nintendo saying, yes, this is a key that Nintendo made up, and it's not just made up by some program that Sega wrote on his computer. There's also a AES key that's used to encrypt the contents of the flash chip, and one that's also used to sign it in a certain way so that you can't just modify it with a chip of some sort. In addition to that, there's a common key, which is really the holy grail. It's what was the root of the encryption used to encrypt everything that the Wii had.
If you have the common key, that means you can read every games and iOS's code, which is very nice because you can analyze it if you can read it. So once you have the common key, you can't change anything, but you can watch, which is very important.
There's also the SD key. In order to keep people from messing around with save files, they used a stupid little key to encrypt stuff on each little save file on an SD card. There's also a root certificate, which is how it does a chain of trust and verifies that the disk you've inserted really did come from Nintendo. And they actually got hip to us, and they tried to reclaim their platform by adding a new key for new Korean Wiis. So they added an additional special Korean key that is only there on Korean Wiis. So where did they actually keep these keys? Well, so they actually hard-coded some of them just inside the binary of the firmware. So you have your SD key, and you have your default common key. This is ridiculous because they actually went to the trouble of buying some expensive silicon to place their secret common key in a hidden spot on the chip, and then they just also happened to include it in all of their firmware images for no apparent reason. Again, this area where they're keeping these keys is this one-time programmable area we mentioned earlier. You have that common key. You also have your ECC private key and many other ones.
You might notice some resemblance here. Not sure why they went to the trouble of actually securing one key when they copied it to the binary. I mean, it's a default key that gets used when the other key is not available, but it's the same key. So
in theory, it only falls back on this key in the factory while it's still being manufactured before it actually gets the serial number assigned. They ran out of space, I guess, for some of these keys, so they added a third little chip inside the actual Hollywood package that stores some slightly less secure keys, but they're still important. So it has the certificate, which was issued by Nintendo and is part of the identity of this console. And also they ran out of room to store their new Korean key, so they actually stuffed it in there as well. And there it is.
Looking at iOS, well, we said it's isolated, the user space processes can't talk to each other except for a defined interface. The kernel communicates with them through system calls, much like you would on a computer. So you could have a process access specific hardware that only it can access. You can do threat management, so it's actually multi-threaded and everything, and multitasking. And you can talk to other processes. The interface is very standard for a microkernel. It's using devices, so it's similar to Linux and Unix. You have /dev/something, and you can open, close, read, write, seek, and IO control, and a little tweak on IO control, which is called IO control V, which is a slight variation. So the devices are set under /dev. For example, ES, which is called e-ticket services, which does all the security stuff, has /dev/ES. DI, which is a drive, has /dev/DI. That's the DVD driver, and it does the hash tree and that stuff. There are many more. You've got USB, SD, network, blah, 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 blah. There are a ton of processes in iOS. Broadway can actually talk to iOS too. The way it does that is it gets marshaled through a little interface, and iOS has a process where everything from the Broadway seems to come from. So when you talk from the Broadway to iOS, everyone else on iOS thinks it's coming from a specific process inside iOS. So they can check for that, which is important. The signatures are all done by one function, which does RSA verification. Well, RSA signatures are done by one function. There's other algorithms in there. The function is called ES_verify_sign, well, main function. It uses a hardware SHA-1 engine, and it uses software RSA. So SHA-1 is accelerated, which is very nice because the disk needs to use it a lot. Meanwhile, RSA is just done in software because it only happens a couple of times. So before loading code, iOS checks that SHA-1 hash and that RSA signature, and if it doesn't match, it just says no. Of course, the SHA-1 is signed by Nintendo, so they get ultimate control about what runs and what doesn't. iOS decrypts the RSA signature, it checks for the real signature, and if it matches, and if they're compared, then it verifies, and we can move on to load the code. For those of you who are not being exposed to crypto, you might think that RSA is some sort of really complicated, takes 1,000 lines of code thing. Well, the code's a little weird because it's big numbers, but you actually learned how to do RSA in high school. I mean, you only need to know how to do exponents and how to do mod, which is just a fancy way of saying take the remainder of a division. So it's big numbers, so there are peculiarities involved, but ultimately, it's really just you get the signature, you do it to the power of the public exponent, and you do mod the public modulus. That's really all there is to it as far as the decryption. A signature is really just the SHA-1 that's being signed, add some constant padding, and then that gets run through RSA, and you end up with the signature. When you decrypt it, you need to come up with the same thing. So you literally take those bytes that make the signature, take this one big binary number, run it through that formula, and then you get out the original signature, and you need to compare it with what you're actually being signed. So Nintendo did RSA in an interesting way. They start off by doing the decryption, which is what you would normally do, it's all right, and then they ignore the padding. Now that doesn't break the security, but it shows that they don't know what they're doing, which is interesting. And then you look at how they compare this SHA-1, which is only a bunch of bytes, only 14 bytes, or 20 bytes, and it looks interesting because so they get the signature and they compare it, and the compare function looks a little bit like comparing strings.
But these are binary numbers.
Yeah. For those of you who don't know, a C string compare function stops on the first null byte, which means if your signature has